So I do have to mention that I went after my PE late in life, late in my career, and knowing what I know now, I would recommend pursuing your EIT even before you get out the door of this place, and gather up those PE contacts because you'll need them to vouch for you, and get your PE as soon as possible. Two good reasons for that. One is it's going to help your career quite a bit, and two, everything will be fresh in your brain still.
Hey Scott, can I offer an endorsement?
Yes.
I promise you guys, I waited 12 years to take mine. I promise you, if you take it right now and you show up not hungover, you're gonna pass. Wait 12 years, you gotta learn integration by parts all over again.
Oh yeah, I took a prep course for 3 months.
Oh, I know, I did too.
And yeah, it's a long test. It's 2 4-hour sessions. So yeah, don't take that lightly. Let's see, I think we already captured that. We'll get to some of those details in a minute, so Blake, go ahead, next one. So here's where it all started. Not even half of you have been in that building. I was a young freshman, and my friend Tony Balistreri, that I had been friends with since 7th grade, we were both at orientation week, and Tony said, hey, my brother Tom is in his fraternity called Sigma Phi Delta. It's way off campus out on 33rd Street. Let's go check it out. I'm like, okay, that sounds great. So we go out there. It's a beautiful late summer day, you know, it's end of August. Tom's showing us around the house, this nice old mansion. All the windows are open, the wind is blowing through there. And I remember going to one of the rooms, it was room 1, and there was this big guy that everybody called Moose, and he's sitting at his desk, he had a pitcher of beer, which he was drinking out of the pitcher, and he was doing a bunch of work. And we met Moose, and I said, this place is really cool. I got to become part of this deal. And so decided to pledge, as did Tony and another guy named Bob Rodriguez, and that leads us to the Lucky 7. And that handsome guy looks like a younger version of me. A lot more hair. But anyway, so that's the Lucky 7. That included Bob, Tony, myself, Bill Haas, Larry Carmody, Mike McGonigal, Brendan McGoldrick. Did I leave anybody out? There's a memory test. So that's the Lucky 7. Most of us are still in contact. A couple of people might be out on the fringes, and we got to keep an eye out for them. So then, of course, we actually had to go to school. And you start your electrical engineering course, for me anyway, and that includes, oh yeah, sorry, next slide. Yeah. That includes taking classes in circuits and digital electronics and some other exciting things. I think many of the people had some exposure to electricity to some extent. I did, just from growing up around my grandfather, who was an electrician, and but this stuff was pretty new. So this was state of the art in 1980. These are 8-bit microprocessors. The one on the left is Intel 8085, and the one on the right is Motorola's competition to that, the 6800. Now these are not microcontrollers, which would have I/O, memory, A to Ds, communications interfaces. These are strictly the processor itself. So one of the things we learned how to do is apply memory to these systems and demultiplux the address data bus. And when you wanted to do a simple thing like add X plus 2 to make Y, you had to go out to the memory, retrieve X, bring it in, load it into a register, go back out to the address of 2, bring that in through the data bus, load it into a register, and then do the arithmetic addition process. And doing anything with these processors was literally that much of a nut and bolt operation, and that was called assembly language. And to talk to the assembler, we'd have these CRT screens that looked like they came out of the 1950s. Somehow we made it work, and we figured out how to use these processors. Now the other thing I'll point out is the size of those processors. That chip is around that long and around that wide. And the processor itself is, and my right shoulder is a little boogered up, but we'll try, is in this part, and the rest of it is just to get out to the pins so that you can interface to the device. So things weren't shrunken down quite as much as they are nowadays. part of being at the College of Engineering, let's see, that'd be freshman, sophomore, junior year, is you can participate in a cooperative education program. And that had the advantage of, and you know, probably some of you guys are involved with this, but for me that had two advantages. One is, instead of sitting in a classroom learning real life engineering and working with real life engineers. And the other thing was making some cash, because those were the days where we'd scrape up quarters and loose dollar bills and put in like three gallons of gas in the tank and have enough to last us a few days, if that. So, you know, the people in, say, dental hygiene or whatever, they got to work, sorry, they got to also work professionally, but they didn't get paid for it. And the guys and women in the cooperative education program, we made some decent money because we worked with 4 major corporations, both regionally and, you know, throughout the world. My buddy Mark Johnson, who was, I think, the class after us, he worked for Naval Research Laboratory in Washington, D.C. And so there were people scattered all over the country, and every other semester you would do that. So here's how I got involved with this. In the 1980s, GM was a huge conglomerate. If you know GM now, they make Cadillacs, Buicks, Chevy and Chevy trucks and that sort of thing, and not much else. So they're a car company. Well, in the 80s and the time period leading up to that, there were 2 things. They were vertically integrated, which means they had subsidiaries that built everything from taillights to carburetors to the air conditioning compressors. It was all vertically integrated. But the other thing was they were a huge conglomerate that had many other companies. For example, you know, we can look up here, North American Aviation, Allison Transmission, Dayton Wright Company was in the, kind of in the aviation business. Delco Electronics was pretty well known. That came out of the Dayton Engineering Laboratories company of Dayton, Ohio, way back, long before any of us. And that was a big part of GM. And you'll see that under E, they have one listed there. It's called Electromotive Diesel, which at the time was called Electromotive Division. Nobody really ever heard of that thing, except for me, because I knew about locomotives a little bit ahead of time, and that's what they built there. And to put it in perspective, so there was a brand of car that GM made called Pontiac, and I'm sure you guys have seen Smokey and the Bandit, right? So you know what a Trans Am is. And Pontiac, because of the Trans Am, in the 70s, they were the highest profit division in all of General Motors. The 3rd highest profit division in all of General Motors was Chevrolet, because, you know, they're huge. They're building trucks, they're building cars, Camaros, all that good stuff. The 2nd highest profit division in all of General Motors was Electromotive Division, that nobody ever heard of. And that's because in the 1970s, they built 5.5 locomotives per day, every day for 10 years. And each of those went for between $200,000 and $250,000. So you multiply that out, they're making several $100 million a year in the 70s, and they made it every year. Next slide, please. So Scott goes through his interview, has a little bit in common with the guy that interviewed him. He says, "Oh, I see you flunked first semester chemistry." And I said, "Well, you know, it was at 8 o'clock, and I'm in a fraternity." Poor excuse. I thought, well, okay, that one's gone. We'll try another one. And he goes, "Yeah, I flunked chemistry too." And next thing you know, Scott works for the Electromotive Division of General Motors, which we'll call EMD. They're located in the southwest suburbs of Chicago in LaGrange, at least they were at the time. That's the factory in the background on 55th and East Avenue. The main plant was about 2 million square feet under roof, and with the other buildings and so forth, there were probably 3.5, 4 million square feet of manufacturing there. And so it was a pretty big deal to the economy down there, and it was kind of a local institution. So I'm from Milwaukee originally. I moved down to the southwest side of Chicago, go to work at GM. Next slide, please. So they build railroad locomotives back in these days, and how does a locomotive work? You know, it's just something that goes down the road, makes a lot of noise, a little smoky sometimes, and that's about it. Well, it's actually a rolling power plant. It's got a guy sitting up here in the cab, the engineer, they still have that, and he's got control inputs that he gives. There is an electrical cabinet up here with the control system and power devices and different things. And then we have a diesel engine that's rated at somewhere between 3,000 and 4,500 horsepower, and a very large generator that's between, say, 2.2 and 3.5 megawatts that's on the same shaft as the diesel engine. So it takes all the power from the diesel, turns it into electricity. Back in those days, it turned it into DC electricity by rectifying that power from the alternator. And then again, that would come through the electrical cabinet where a miracle occurs, and it would go down to the wheels. Now each of these is a solid axle wheel set. So you've got 6 axles. Each axle has a large DC motor on it called a traction motor. And that technology has been around since the 1920s. Then of course you have auxiliary systems. You've got your radiators and oil coolers and all the things that go with large engines, and lots of blowers to keep all the electrical components cool because they generate quite a bit of heat. Next slide, please. So how do we use these things? And either you get stuck at a railroad crossing and you go, oh damn, I'm late, or you go, oh, this is kind of neat, let's see what's coming by, which is me and nobody else. And always thrills my wife. So what you do is you take one or more locomotives, you put them together in a consist, and then you hook that up to a train that might weigh 5,000 tons, 10,000 tons, 15,000 tons, which is a lot of weight to pull. And then these locomotives use all that power to produce tractive effort. So at the last unit here, at the coupler to the train, that might be 300, 400, 500,000 pounds of tractive effort pulling on that train, keeping that moving. And as you can imagine, starting that much weight takes a little bit of effort. And then as you speed up, now less effort is required, but then more horsepower is required to keep it moving. So that's what these locomotives do. They plug them together, and they don't fight each other because they're just really all pulling behind them. To go into statics and dynamics, all the torque vectors align the same way, and they all basically add up at the last coupler in the consist. Let's see, how else? They don't stay very clean, but that's a different story. Anyway, let's move on and we'll get into some fun stuff. So in the 70s, we had some pretty high technology. They took the controls portion of this electrical cabinet and they modularized it. And the reason they did that is to make maintenance easier. When something wasn't operating properly, the technician could at least look up which module might be at fault through a troubleshooting guide, pull the thing out of the cabinet, plug another one in, and hope that it fixed the problem. So as you can see, these modules had these very tiny resistors, which are about that big, capacitors, relays. You know, the components were rather large back then. These things weighed a few pounds each, and that was the tech in the 70s. Next slide, please. So all of these things stacked together in this part of the electrical cabinet. Up above, behind the doors, was filled with large relays. They used relay logic. Back before computer logic and computerization, they used relays. One of the reasons that they were so slow to change is because it's an old industry, very entrenched in its ways, and everybody says, how are we going to trust those little chips to control something this big? We can't see what it's doing. What if it goes crazy? We just don't understand it. So they stuck with relays for a long time. And that even held true in other parts of the industry. The signaling system, if you pay attention, you'll see, when you look down the tracks, you'll see the signal lights. Those systems ran off of relays up until the 90s because they definitely didn't trust computers to run the safety systems because, again, well, you can't see what those electrons are doing. It's software. We don't understand that. So we had to overcome those things as we applied more and more technology. Next slide, please. So that brings us to the 60 series project at EMD. We were competing against another company whose name starts with General, and they were like the minority supplier, like 20% of the market. EMD had 80% of the world market building locomotives. But GE was actually catching up and maybe getting a little bit ahead, and the people at EMD were very alarmed by this, as were the people at General Motors corporate. So they started a project and injected hundreds of millions of dollars into EMD to computerize the locomotive and compete with the other General, and also just to stay up with current technology, because the automotive side was doing that as well. So that started the 60 series project, where we endeavored to computerize, and to this day, some people in that industry still call it, oh, that's a microprocessor locomotive. It's like, well, your phone has it on there too. But that was that project, and that started in about 1983. So let's go back to these awesome 8-bit microprocessors. This is the spec on the CPU that we used in those units. So you can see the processor itself. So GM had a deal with Motorola. They used the 6800 series. The 6803 was special to General Motors, and so we had to use the 6803, which is fine. And you can see it had these following amazing characteristics. It had a 16-bit address bus, 16 bits, 8-bit data bus, and a couple of other ports, an 8-bit I/O port. It ran at a whopping 8 megahertz. I don't know what your phone runs at, probably 100 megahertz, I don't even know. Yeah, so pretty crazy. Now, the other thing is, since we had to have external memory, because I said those chips were not microcontrollers, you can see that they had a whole 4K of random access memory available. So think of, so we have here however many gig is on this thing, and that's just a little blob inside of this thing. We had 4K memory chips. So one of the things about that is when you're writing software and you have 4K available, you better write some really efficient software. There's no room for compilers and waste in your software. And we'll look at that on the next page. Let's not forget the routines that run this. There are a whole bunch of different functions that have to take place on these locomotives. And the major routines, they call it wheel creep. Basically, it's wheel slip. We'll talk about that in just a minute. Then we have load control. You've got the guy saying, hey, I want step 2 on the throttle, and it's a 3,000 horsepower engine. Well, how many horsepower are we going to put out? How are we going to control that? There's the whole thing about the load curve and how smoothly you apply it. That all has to take place. Locomotives have a thing called dynamic braking, where they can take the traction motors that I talked about on the axles, convert them into small DC generators by reversing the fields, moving that out through resistant grids and dissipating it as heat. So instead of grinding the brake shoes going down a hill, you can go into dynamic braking, throw that all out the roof as heat. So you have all these routines that go on, and every one of those is several hundred pages of assembly code that these guys had to write. There was a whole room full of people like this that sat there all day doing nothing but writing code for these things. And we didn't have C yet, or C+, or C++, or any of those awesome things. So it was done the hard way. Here's one of the typical modules from the 60 series. You remember I showed you those red-faced modules in the earlier units. Well, we upgraded. They got a little bit skinnier. The parts got a little bit smaller. You can see we've got some chips on there. Again, by today's standards, this stuff's all huge. These are dual inline pin chips. So they have 8 or 16 pins. The size of the boards, the layers went up to multiple layers. You see ground planes on here to keep the noise away. So it was a big jump in technology from some of that 70s stuff. And then we had a whole cabinet full of these modules to do the job, and we'll get into what some of those do. So here's just a line diagram of the logic control. As you can imagine, we need inputs from a lot of different places. So we're looking at main generator voltage and current, what's going on with the traction motors, the engine speed, temperatures, input from digital sources. So they use switchgear to control what's going on from the generator to these motors through these big DC cables. So that all comes in. You have to operate the switch gear. So you've got input, output, you've got feedback, which is doing the processing, because these signals always come in some form that has to be processed to get them down into the computer side of things. And you get it all crunched down into the CPU. And the thing about this system was the 6803 didn't have enough horsepower, pardon the pun, to really run this 3,800 horsepower locomotive. So they used a system with 3 different control sections or chassis, and each one of them had a CPU in it. So we had 3 of these big 6803s in there running things. And then they all talked together through a thing called the common memory, where they decided it would be more practical to have all these 4K memory chips stacked up in one central place and then have the communication between the units. And so the same thing happened. That was the logic control. Here's the excitation control. Again, you have this big generator that's spinning from the diesel engine. The way you control what's coming out of that is by exciting the generator. And in like an AC generator that you might see in power gen, that has an exciter on it, you put some kind of signal in there. On a big DC generator, it's done a little bit differently, where they directly excite the coils using some SCR technology. And the thing about that is you have to have angle-based control. When you fire an SCR, you have to gate the SCR at the right time. So none of this is time-based, this is all angle-based, which back then, to go from time-based processing and use sensors to convert it to angle-based was a pretty big trick, especially with the lower level languages that we're using. So that all happened. Again, we had feedback, we had excitation control, another CPU, firing. We just talked about the firing, that was fairly complex. We'll get to this radar thing in just a minute. And then I mentioned the SCR, silicon control rectifier bridge, that fired the main generator. So that's how you get from 3,000 horsepower diesel to having a control input, is you go through that whole process. So I mentioned these traction motors that are down on the axles. Again, it's a solid axle. These motors would actually hang on the axle. So the axle actually went through here like that. This is a large DC motor between 750 and 1,000 horsepower. So that would be about this big. I think they weigh somewhere in the 10,000 pound range because it's full of copper. At the time, EMD was the largest consumer of copper in the world because they manufactured all their own generators and motors. So these are direct current motors. They're series wound, which is significant because that affects how they're used and how the torque curve works. They have a reversible field, which is important because that's how you make the thing go either direction, is you swap the field. And it's also important for braking, which we won't get into how the braking works too much. But all of those things are characteristics of this motor. They have a huge commutator, that's on the left side over here, and brushes. And these are all things that are high maintenance items that once we jump forward beyond this presentation, it all becomes obsolete thanks to the miracle of power electronics and AC. But at the time, that was state of the art, and those were all manufactured at EMD. And it was a big deal because that was kind of the Achilles heel of the locomotive. They could make horsepower all day, but getting it down to the wheels and keeping it from overheating and making it behave properly, that was a whole control trick. And, oops, one back, please. Oh, okay, no, you're right. So that motor, the thing about that motor, and Bob pointed this out to me, this is 1982, 83. Personal computers were just maybe coming in and showing up in the office. Email was like a new thing. I know that sounds insane, but that's the way it was back then. And when you wanted to make a curve on one of these motors, you didn't plug in a bunch of data loggers and sensors and run it through a computerized test. You put meters on this thing and you ran it through its paces and you got a piece of graph paper out and you started graphing. And that's what we did. And So we did two things that were important. This is the current versus terminal voltage curve. And because that depends on load, you get a bunch of different lines on the curve. And using the typical application on a locomotive with a gear ratio of 62 to 15, and knowing some of the other characteristics, they could plot this curve out for a given horsepower. And you can see I've got some notes on here where I did some different things, because I pulled this right out of one of my notebooks. But it was important to know at any given time, at a given speed and horsepower, what the current and voltage is, because that's really the lifeblood of the motor. You had to operate it within the range of its current capability, and you had to keep it within the voltage range. Now on this side, this is the torque curve for the motor, and this is something I've spent enough time with that it would put you all to sleep probably. The important thing about the torque curve is, as the current goes up, the tractive effort goes up. It's, you know, after you get out of the gate, it's fairly linear, and that's why DC motors were used for so long to do things like run locomotives and other torque intensive loads, is because they were perfect for it. The more current you had, the more torque you had, and that's the characteristic of a series wound DC motor. So there were groups of people that they lived this their whole life, just improving this curve and tracking the motor characteristics. And what was important about that is you had to, if a locomotive is 3,000 horsepower, the motors had to be able to withstand that horsepower. So all these curves fed into how that was all designed to work together. Now we get to adhesion. Looking at that last curve I just had, you can see that if you applied a lot of current, you had a lot of torque. Well, the thing is, the reason railroads are so efficient is it's steel wheel on steel rail. There's no friction. You think of pushing a truck, if you guys all got behind a stranded semi and pushed it down the road for a little bit, or a city bus in the case of what we did on 33rd Street that one winter, it's not going to roll very far. You've got these rubber tires on there and you got cement, and it'll roll a little bit and it'll stop. You can get behind a freight car and give it a shove on level track and it'll go for miles. That's the efficiency of railroads. That's why, and they were very smart about this in the last 10, 15 years. As that became important, they've really tried to sell that concept as, hey, you know, you might not like these noisy locomotives coming through your neighborhood, but this is very efficient. It's a very green method of transportation, and that's because of steel wheel and steel rail. However, steel on steel is a little slippery, especially when it rains or you get some leaves on there or whatever. So they have this concept called adhesion, and it's really easy. It's just the weight of the locomotive versus what you're pulling at the coupler. If the locomotive weighs 400,000 pounds, which is typical of a big 6-axle locomotive at the time, 200 tons, then if it had 25% adhesion, it was pulling, let's do some higher math, 100,000 pounds. And that is the adhesion formula. And the easiest way to get more adhesion is put more weight on it. But there's a limit to how much weight you can have before you start tearing up the infrastructure. So then it comes down to how do we control this to keep it from slipping? And there are different philosophies of doing that. Some companies have done it by sensing the speed of the motor itself and seeing if they all match, and if they don't, one must be slipping. Some companies have looked at other characteristics and compare them to see, and the smart people at EMD came up with a concept where they calculated the motor speed based on the electrical parameters and figured out one other thing to throw in there that we'll get to. But before we get there, they came up with this concept. The guy's name was Chuck Logston Jr., and he got an award from General Motors for thinking of this. They came up with what's called controlled creep. What they found is as the wheel spun faster than it was moving on the rail, to a certain extent, you would maximize friction. And maximum friction means maximum traction. And they found out that you could spin the wheel up to, say, 4 or 5% higher than track speed, and you'd get up on this curve, and these things would just pull the crap out of stuff. And the reason railroads want you to be able to do that is because if you have 3 locomotives that can pull as hard as 4 locomotives, you don't need that 4th locomotive. Now, if you've got a fleet of 1,000 locomotives and you can take 250 out, you're saving a lot of money, both on cost of ownership, leases, maintenance, all of that good stuff. So traction is a big deal to these railroads. You get unit replacement out of that. The people at EMD came up with the secret weapon. They said, hey, what if we knew what true track speed was? Now we can figure out how fast the motors are supposed to be spinning and just put an easy equation in there and say, hey, spin up to this much higher than track speed. So they came up with an X-band radar. It was one of the first projects I worked on as a co-op student, is testing these things. And at the time, every locomotive had a radar mounted under, so you can see here's like the bearing on the wheels, and that's the pilot. There's the steps where the guy goes up to the cab. Had a radar mounted underneath there looking at the tracks, and it would calculate the track speed of the locomotive from the radar. And when it worked, it blew everybody away, and GE couldn't, the other general, they could not catch up to that concept at all. It was a big competitive advantage. Then people started thinking, well, besides who's this dork on the front of the Union Pacific locomotive, they started thinking, what if we could take these older units and improve them? So I said, in the 70s, GM produced 5.5 units a day, every day for 10 years. The legacy fleet out there were tens of thousands of these units from the 70s that could not perform as capably as the newer units. And people had different philosophies. They said, well, let's put our own version of a microprocessor control system and retrofit the whole locomotive. Or let's at least come up with some traction controls we could put on there for some price, and that would pay for itself because the locomotive could pull harder and you'd get the unit replacement. The rest of the advantages of having computerized control and diagnostics and other things wasn't as big of a factor really as that traction control. That was what everybody really zeroed in on. So people became very interested in upgrading the legacy fleet. So what happened was there were several, probably 5, 6 companies, they specialized in rebuilding older locomotives. Again, these locomotives from the 70s. That could be done because these things live forever. They were all heavy steel underframes. They had lifespans of over 30 years. And they would do what's called a capital rebuild. And there were financial advantages to doing a capital rebuild in the leasing business. And the financial stuff is beyond me, but they had a lot of advantages for doing that. About this time, I decided it was time for a change for me. So I went to one of these rebuild companies called Morrison Knudsen. And here's just a photo from outside our locomotive shop in Pennsylvania. We were rebuilding these locomotives for Southern Pacific and making some passenger locomotives for the Virginia Railway Express, which runs out of the DC area. And those were made out of older locomotives. And here I am, we're delivering one of these in service. They had some initial production issues, let's say, and they wanted an engineer to be on board with these things when they're getting delivered, make sure they had no problems. So I would spend my Saturday mornings drinking some coffee and shaking off Friday night a little bit and go down to the railroad yard and jump on our new locomotive, and we'd go down the track and I'd go for a ride for 8 hours. It was pretty, I was what, 27, 28 years old. Pretty good way to have a living there, doing that for a living. So I did that. And then that same company was also working on one of these retrofit computerized systems. And I was working with that, and I didn't like the way they were proceeding. I thought there were maybe some better ways to do it and some markets that would be better. And their philosophy was borrowing from some technology that I didn't really care for. So myself and a couple other guys, we said, hey, we could do this better. Let's leave here and start a company. And that sounded like a pretty good idea. And this was a schematic diagram from one of those red-faced modules on the older technology, the wheel slip module. You can see a lot of high-tech relays and transistors and things. It's just good old analog electronics, nothing wrong with it. It worked good for many years. But there's there's a way to make that better. And again, we have a block diagram of the excitation system on one of these things. And I'm always thinking, well, what can we do here to make this thing perform better? So one night, on a Friday night in Boise, Idaho, I'm in my friend Bill's garage. He's one of the people that we started this company with. And we were drinking beer, and then we had some more beer. We had a little bit more beer. And at some point, after midnight, I found a whiteboard that he had, and I said, I have an idea for a traction control module that would retrofit into one of these old locomotives, and you wouldn't have to change anything else. You wouldn't have to rewire this thing. You could have it installed in maybe 6 hours, which is nothing. And so we sketched this all out, and I worked my way home. And the next morning I woke up and got rid of my headache, and I called him up, and I said, let's go look at that again. And we looked at it, and I said, holy crap, this could work. And that's where ideas come from sometimes. Thanks to beer. Now the other part of this too is, so now we start a company, right? We've got 3 people. We got to get paid somehow. We weren't wealthy. We have to do development. We have to buy parts, that sort of thing. So this same guy whose garage it was, he knew a bunch of suppliers in Chicago of the railroad industry. He found a guy that was willing to throw in $2-3 million into this startup company because he kind of liked our idea, and I think he had a grudge against some of the other players, so he was able to take out his frustrations by helping us out. So we started a company. We called it NOMBA, N-O-M-B-A. And the reason we called it that is because at the time in the 80s, there was a big thing going on where the Harvard MBAs were taking over the world and taking over all the big companies. And they had taken over the company that we left, Morrison Knudsen, and we felt that the Harvard MBAs, and no offense to MBAs, by the way, but the Harvard MBAs were driving this company into the ground. And these are the same people that were responsible for things like, there was a big scandal about an energy company called Enron back in those days. Those were those same people. So we called our company NAMBA, no MBA. And we started that company. That is no shit. Then the lawyers like to get involved. And you can see right here, Morrison Knudsen versus Scott Mann, NAMBA, and John Doe is 1 through 10, whoever they are. The former company said, well, you couldn't possibly have thought of that on your own. You must have stolen our technology. And we said, we all worked at EMD long before you guys were anything, and we worked on these traction controls. You're full of it. So we had a big lawsuit. That's why in the very beginning about being an expert witness in district court, I had to be, because I was testifying on my own behalf. The happy ending of this is I knew they were appropriating some technology on their system. So when we were doing discovery, I called some of that out. They realized they weren't going to look very good. We came to a settlement where we gave them a special deal on our product, which we were making large profits on eventually anyway. So everybody was happy. So we got rid of that. But yeah, the lawyers always like to get involved. No offense to any lawyers here. Okay, we have a company, we want to build a product and do things with it. First, we have to develop something. So we have our makeshift laboratory with this handsome gentleman here, and he's got his oscilloscope and some power supplies and different things. And we breadboard some circuits, and we program some chips, and we start experimenting. And we come up with something that on the bench looks like it would do what it needs to do. That's what we do first. Next, we have something that's good enough that we think we could plug it into a locomotive and test it. Well, how are you going to do that? You can't just walk up to a locomotive or ask, go buy one or something. So you have to find a partner. So we found the Burlington Northern Railroad, which is now Burlington Northern Santa Fe. And this photo was taken in West Burlington, Iowa, which was a big back shop for them. And we got them to work with us to develop this system. They thought, well, that'd be a great advantage for them, so it was worth their time. And of course, it helped us out. So I spent months on the 7874, and what we would do is we would drag the other locomotives up and down the track, simulating a heavy freight train, and we would hammer the hell out of that locomotive and see if we could make it slip and then control the slip. And we did that for quite a while. So this is an actual photo of inside of that locomotive or something like it. So we've got our module here that we're experimenting with. We've got it on an extender card, so it's sticking out so we can access test points and different things. We've got our high-tech CRT battery-powered oscilloscope. A couple of fluke meters. I still have that meter sitting in my shop today. And the state-of-the-art in laptop computers at the time. And we would go up and down the track. We'd identify some things that needed to be changed. We would fix the program. It was written in a language called Forth, which I don't even know where it came from or whatever happened to it. But it was important for a little while. And we would recompile the program and dump it into a processor board that piggybacked onto the main board here. That ended up being a product that we called MaxiTrax. And MaxiTrax was super high tech because it had an RS-232 port on the front. It had a 4-line LCD display that lit up. And then we used a little menu system with a move and a select button to go around and look at different parameters. And then on this side, you can see we have things coming in. This had a bunch of high voltages from the traction motors through the ventilation amplifiers. We had current signals coming in from current transductors that had to come through some transformers to get stepped down. And all these signals came in and were made the correct type of signal to go on to the processor board, which had all of the analog I/O and digital I/O and the processing, and of course, the memory chip. And you had a power supply on there to take the locomotive power, which that's a different subject, but locomotives run off of 74 volts where your car runs off of 12 volts. And so we had to get that from 74 down to usable voltages for the chips and the parts on there. So that was MaxiTrax, that was the product we developed. Now you've got to demonstrate the product. You've got to find people that you're trying to get interested in this product. So here we are up at the Wisconsin Central in Stevens Point with one of my favorite trucks I ever had installing the system on the 6629 that we demonstrated for them. Next, please. One of the cool things about this job was we were selling all over the world. I spent 2 weeks on the South Island of New Zealand demonstrating the system to New Zealand Rail, which at the time was called Transrail, but the locomotive still said New Zealand. So that's actually the Pacific Ocean out there. We're on a coal train running up and down the coast of the South Island. We're looking out the window, watching pods of whales out in the ocean doing this. And the guy said, you know, tourists spend like thousands of dollars to come and see this. And we just look at it every day while we're going up and down the track. So that was a pretty cool trip. And then finally, success, we were on the former Rio Grande, at the time Southern Pacific, now it's something else, railroad in Colorado on what's called Tennessee Pass, which was then the highest piece of railroad in North America. It ran up to 10,300 feet into the mountains. And we had head-to-head competitions with other manufacturers of retrofit devices, as well as our former employer, EMD, that made a retrofit, and we all pulled all of them. And so the VP of Transportation came out with a big smile and said, works as advertised, you got it. So then we have sales. The first year after that test, we sold 240 units to Southern Pacific Railroad. And those units went for thousands of dollars, and the profit margin was very high, so the investors were very happy. We'll just leave those numbers where they are. So that's what it looks like. It's amongst all the 1970s technology, and then we have our new technology plugged in, riding along with it, very happy. And they started retrofitting their fleet. We sold to other companies, and everything went great. And for me, the biggest reward of all, besides making a little bit of money, is my first US patent. There are some people in the room here that have over 100, which is pretty cool. But I bet even his first patent was pretty exciting. And so this was mine. It was me, a guy I work with named Dave, and assigned to our distributor company, G&G Locotronics. But I still have a plaque of that on my wall because that was my first one. So it was pretty cool. Oh boy, then what happens? Well, we have more ideas about other ways to control locomotives and other things we can do with them. But the investors go, wow, I just made a ton of money. I don't know if you guys can pull that off again. I'm out of here. So they leave. now what do you do? I gotta do something for a living, and I'm good at working on locomotives. We think of some new ideas. So NABA goes away because everybody went away. But the core people that had started this thing, we stuck together. We found somebody new to form a partnership with. You'll remember on one of those earlier slides, the different parts of General Motors, the Dayton Electronic Laboratories. There was a division called Delco Electric Motors in Dayton, Ohio. They had some former employees that bought that, and they called it the Dayton Phoenix Group. Well, they had an interest in what we were talking about. They were a supplier also to railroads, and we got to know them. So we started another company that did not have a clever name, so we won't go into it, and we did some more development. We leased a locomotive, which was $300 a day from Helm Financial Corporation, and that sat in the siding in downtown Palmyra, Wisconsin, about 5 minutes from where I live right now, for about a year and a half, and we did development there. And you're thinking, well, you know, you got a little bit of track, you can run back and forth a little bit, but what are you gonna do? Well, the answer is, these locomotives have a way to reconfigure all the power circuits. Up here are our big resistor grids. I told you about that dynamic braking concept. Well, you can configure the locomotive to run at full horsepower and take everything out of that generator and put it out of the braking grids on the top without moving an inch. And that allows you to develop over 80% of the different controls going on before you even have to move this thing. So, let me flip ahead. Here we are again. You know, we've got all our 70s modules here, only now we're taking these out and we're computerizing them. And in this case, I fell in love with this little computer chip. It was made by a company called Microchip, and it was their PIC series. 16C72 was really popular. These chips had pretty good memory. You could write a program in BASIC and compile it onto the chip. You know, none of this assembly stuff. Let's write it in high level. And they had I/O and they had communications. And I said, well, if we computerize the modules individually and give them some intelligence, some troubleshooting ability, even if we just had a green and a red light, and the red light went on when it thought something was wrong, you know, that would help the railroads out quite a bit. So now we're back into doing development again and building things. So this is not quite in production, but this is the VR2000. This all took place coming up to the year 2000, and everybody was all into that whole flipping into 2000 thing. And you'll notice that the locomotive was numbered 2000 as well. And so here we have replacing some of the 70s analog electronics with some updated stuff. Here's the PIC Micro. And one of the other things on here, a big thing that happened going into this time period was the power semiconductors really started to improve capability and become lower in price. So instead of all these transistor cascading combinations and all kinds of crazy things, we could buy one IGBT, insulated gate bijunction polar transistor, and put that on there and let the IGBT do all the work. And the controls for it were pretty easy because you could put a pulse width modulator into that thing and let it do what it had to do. In this case, it was exciting an auxiliary generator to make that locomotive control voltage. I should have added that at first, but it didn't matter because the whole idea was computer chip, newer components, bigger power components. Hey, this could be a pretty good thing. One of the things that was kind of interesting for anybody who is electrical and is getting into control systems at all is nowadays tuning a PID loop is fairly simple, especially if you have a program like Simulink or something. Back in those days, tuning a PID loop was a little more complex, especially if you had to recompile the program every time. Changing the gain on something wasn't always easy. So in this case, I cheated and I put 3 knobs on the front of the thing, ran them into A to Ds, and was able to change the gains on the fly. Nowadays, we wouldn't have to do something like that. So that seemed like a great idea, but oh, what happened? A couple things happened. Once again, investors got nervous because they thought we would just start churning out millions of dollars pretty quickly. The other thing that happened were market conditions we couldn't escape. There were mergers in the railroad industry. Every time railroads merge, one of the things that happens is the fleet size gets reduced. So you have all these locomotives not being used. So the last thing anybody wants to do is upgrade a bunch of old junk when they're rationalizing their fleets after a merger. They're under pressure from the stockholders to save a ton of money, so that's what they do. something else happened that was an even bigger impact, and that's the Environmental Protection Agency. You know, if you think about automobiles from the 70s, I have a 72 Buick that just spews out hydrocarbons. You have to change your clothes when you're done driving it because it just smells like exhaust. It's awesome. Cars nowadays put out virtually no exhaust to speak of. I mean, they're not perfect, but compared to the old cars, they are. And even by that time, on-highway diesels were going up in emissions, tier 1, tier 2, tier 3 emissions. Everything is now tier 4. They're already looking up to tier 6 and beyond. And it's the same thing, you know, keeping the emissions down. Well, they decided the next thing to go after would be heavy equipment and off-highway diesels, and that included locomotives. Well, the 70s locomotive engines were considered tier 0 and gross polluters, and they spewed out lots of really good smoke. And by this time, at least they were up to tier 2 and cleaning things up quite a bit. So now, we've got these old locomotives, we can get them cheap, but the EPA is gonna outlaw them anyway. Let's start investing in brand new locomotives and technology. So all of a sudden, in a matter of like a year, the market dried up and the whole concept went away. And the writing was on the wall. It's time for Scott to think about something else to do. So went into natural gas, spark ignited engines for power gen and mechanical drive, so big stationary engines, kind of similar. Horsepower range from 1,500 to 4,000. Still fun to work on. And this happened to be a company based out of Waukesha here, which you can see on the manifold Waukesha engine. They later became part of General Electric, and that'll be a different presentation on how that all worked out. But needless to say, no more locomotives after that. Spent many years working on natural gas engines. A couple more patents that I'm very proud of. And time moves on, and now I work on other things. Still into electrical engineering, more into three-phase power and power electronics, and that never really leaves, but just how it gets implemented and what you're working on at the time changes. I think the lesson there is don't get entrenched in something. When things change, don't take it as a bad thing. Take it as opportunity. Pivot, I think, is the word everybody uses now. That's why I had to put it up there. You do that, you do something else, you keep going. You keep learning, keep producing, and you'll always be happy. So I think that's the last one. There we go. So, I know you wanted to spend a lot more time on the motor curves. I know you did. Any questions? Yes, sir, Mr. Fleckenstein.
Yeah, so I'm a mechanical. So I was thinking all this time you're talking about slip. Is that wearing out the tracks and the wheels on the motor?
Yes, it does wear out both the wheels and the track. And the brilliant guys that invented that controlled creep, after about 4 or 5 years, it backfired because the mechanical department said, we're replacing these wheels all the time. What the hell is going on? And the maintenance away department said, why is the railhead on my track wearing down so much in certain areas? So the benefits that the operating department got from being able to pull more freight didn't work out so well for the other departments. And that became kind of a bad thing.
Do they balance those two then? To kind of hit this creep that you programmed in?
To this day, you could still, where I work in Waukesha now is on the Canadian National Main Line pulling out of town, going uphill. You can still hear, when these wheels are creeping, they make like a high-pitched singing noise. You can still hear them doing that when they're coming up the hill, but not to the extent that they did when they first implemented this. They dialed it pretty far back to try to keep everybody happy. Yes, sir, Robert.
So as you start introducing integrated circuits, computer circuits, I know the original infrastructure of a train is extremely noisy electronically.
Yes.
Not to mention it's dirty as all get out, greasy place. How did you?
That is a great question, and so a couple things. The other thing besides that is, and the railroaders are more than happy to tell you, well, we operate in the worst environment there is. So, and they do to some extent. In Alaska, they have railroads. They'll run at -40. In Mexico, they have railroads. It'll be 120 degrees outside. You go through a tunnel where the air gets superheated from the exhaust of the locomotives. It gets up to 180 in there. So part of implementing all this was finding the hardened components to do it. Everything that was used was military spec or better. There was some, I think there's a level above that, maybe that they use in some satellites and different things, got pretty expensive, but at least mil spec was the minimum spec for these components. And that gave you your temperature range and your vibration characteristics, because there's also a lot of vibration. And all of those boards that I showed you are coated with what's called conformal coating. So even if the air, the cooling air that's blowing through that system cabinet is kind of dirty, it's not gonna get in there and cause short circuits or pollute anything. It's gonna just blow right by, because that coating protects all the electronics. But all of that was key, and we spent untold hours, days, and years putting these things through environmental chambers for heat, cold, moisture, vibration. That whole thing, now it's called highly accelerated life cycle testing, HALT testing. That was something that we were on the cutting edge, because this stuff had to get out there and it couldn't fail, because our reputation would be gone in a minute. So that was a big part of it. Excellent question, thank you. Okay, must be Miller time. Oh wait.
You guys, when you first partnered with that railroad company to kind of develop your idea, how did you protect your intellectual property, like during that testing and partnership with them?
The business side of our company came up with some kind of agreement and signed it with the railroad. And by then, of course, we had good lawyers, because we had just defended ourselves. And between the business guys and the lawyers, they got whatever they had to get written up to do the IP protection, which is very important, of course, and nowadays is even more important because of other entities around the world that might like your technology. And also part of that was we wanted to make sure that they felt they were getting benefit out of it as well. So that's a big side of that business. You know, engineering is all fun and games, but the other part with all the paperwork and the agreements all has to happen too. Yes, sir.
Why did you leave General Motors first time? Or like when you went to that company that ended up saying
it wasn't so much that I disliked General Motors. Part of it was that I had worked in LaGrange for a long time, and I was pretty young. I was in my early to mid-20s, and I had gotten a little taste of the life of being on the service department, going around and traveling and riding locomotives and fixing problems on the road. And I really liked that, and I wanted to travel around. I had nothing holding me back. And I tried for almost a year to get into the service department to do just that. And this will happen a lot in places you work. I had a boss who was kind of a jerk, and he said, well, as soon as I can replace you, I'll let you go and you can do that. But he didn't try to replace me. And after a year, I finally gave up, and I said, you know what, I'm just gonna leave, and I'll find something else, because I wanna do that, you won't let me do it. So I tried to get it worked out. I tried to work through other channels, through the department I was trying to go to. GM was, and probably still is, a pretty huge bureaucracy, and I just couldn't make it happen. So when all else fails, you change and you do something else. Yes, sir.
I was just going to ask, do you know how long before GE left Waukesha Engine and Z left?
I was there 5 years under GE and had some stock that got vested and left the next day, because when GE bought Waukesha Engine, and again, this is GE Energy, not GE Medical, so don't, I'm not saying anything bad about other parts of GE. GE Energy bought Waukesha Engine and brought in all these things like 40 hours. Out of 40 hours in a week, I bet I spent 26 hours in meetings. And somebody else sitting over there that I'm married to, I met her there, and she can testify to that. Hey, how come you're not getting your work done? I said, why don't you have another meeting to discuss it? Let's get it up to 30 hours. And that was the project management phases were just insane. Nobody could work on the project because you're always in project management reviews. And it was, the other thing about it, before GE bought Waukesha, it was a company where you could walk down the hallway and the chairman of Dresser Industries that owned Waukesha, he'd walk up, shake your hand, and call you by name. When GE took over, you'd walk past the boss's boss's boss, whoever the newest guy was in charge of GE Energy, and he would look away and wouldn't even talk to you because it was too damn important. I said, yep, not for me. So you'll have that. I liked working there a lot. It's just like I liked working at EMD, but when things aren't going the way you want your career to go, you move on to some better opportunities when they come up. And that's what happened.
Seems like they're still recovering from GE a little bit.
I think there are many people that are. You know, in all fairness, I have a nephew that works for GE Medical. He's doing great. He likes it. Again, there are parts of that company that are great. I think gas turbine is probably pretty good, and jet engine. The energy and the power and water, I think maybe had some issues going on. They even spun off their transportation division, which was where they built locomotives, to another company. So, you know, these companies, just like GM, decided to focus on automobiles and nothing else. GE started to focus on their core businesses, and things change. And those marketplace influences will always happen. Okay, now it's Miller time.